But even Pythagoras, like he had the monochord and then he was dividing the
Yeah,
monochord
like
into different ratios.
it's in the physical world. They used geometry to solve problem in the physical world. That's exactly math and physics.
Does math exist? What was the
Independently of
Yeah,
humans.
Independently of humans.
Independently of somebody thinking of it. Like, does it exist before you think about it?
The Galileo, the Italian guy who in 17th century was throwing rocks from the tower.
Dropping rocks very carefully. If you throw them, it doesn't work.
It all depends on the sponsors, so be careful.
In this episode, the 632 Nanometer podcast teams up with Daniel Aronovich from Data Science Decoded. Daniel, Xinghui, Misha, and Mike discuss Eugene Wigner's essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Follow along as they ponder the secrets of the universe, break down the key points of the essay, and go off on various entertaining tangents.
So today we're going to discuss the unreasonable effectiveness of mathematics in the natural sciences, which is an essay by Eugene Wigner. And he explores the profound and somewhat strange relationship between mathematics and the natural sciences. He begins by noting that mathematical concepts often appear in contexts where their relevance is entirely unexpected, but remarkably accurate in describing physics or natural phenomena in general. Then he introduces two central ideas. So first, the success of mathematics is providing a precise description of physical reality. And secondly, there's a concern that this success might not be unique. So there could be other entirely different mathematical frameworks that describe the world just as effectively. So in order to do his discussion, he defines then what he thinks mathematics is, and he describes mathematics as a discipline concerned with the invention of concepts. So it's a creative pursuit, and these concepts are not necessarily inspired by physical reality, but are defined in ways that allow for manipulation and theoretical development, oftentimes guided by beauty. Physics, on the other hand, is the study of the laws of inanimate nature, seeking regularities in a complex and often unpredictable world. So the essay then goes on to discuss the role of mathematics in physics, emphasizing in particular that mathematical concepts are not just tools, but foundational to the formulation of physical laws. So Wigner highlights the fact that many mathematical structures, such as complex numbers and Hilbert spaces, were originally independently developed of physical considerations. However, they turned out to be indispensable in modern physics, in particular in quantum mechanics. Then Wigner concludes by contemplating whether the success of the mathematical framework in physics is truly surprising, or if it might be a reflection of the physicists' what he calls laziness to use mathematics to describe the world. All right, guys, let's discuss. I mean, we all have a scientific background, and we have all used math to describe what we do to a degree.
Yeah, I think he starts with this example, this toy example of a student that's talking to another student that's doing statistics, and he says, what is this pi? Like, why is pi here?
In a normal distribution, why there's pi, which is weird.
Exactly.
Because pi is typically, it's like, in geometry where it's related to the circle, to the ratio of the circumference to the diameter.
And he says, surely the population has nothing to do with the circumference of the circle.
But who knows why there's pi in a Gaussian distribution?
I mean, when I see pi in places, I just assume that there must be some kind of cycle involved, right? That there is some cyclical process, and so therefore pi is in there. That's kind of always my interpretation. Like, how does it actually end up in there? That's a good question. Is it that the normal distribution, it is kind of cyclical because it starts very, the numbers start small, then they go up and back down. So it's probably just, you can turn it into a circle.
From mathematics, it just comes from taking the integral of exponent. And then if you do the math, that's what the exercise I did. I remember in my first or second year.
Why the Gaussian distribution is the integral of exponent?
The Gaussian what is it? Oh, because you have essentially there's like exponent and then minus x squared divided by 2 sigma.
Okay.
So then if you do the integral over from minus infinity to plus infinity, then you need to make a trick. You need to multiply with x squared plus y squared, transition to polar space, and then in the polar space you integrate it and you get a pi.
This is exactly the paper. Why is this
why would
related?
that work? Why would that work for the norm? So what's the normal distribution? Normal distribution is basically just the statement that, if you say it in plain language, it's just a statement that as you depart further from the average, the chances that you exist are lower, right? Like basically. So if the average is x, the chances that you exist are 67% chance that you exist within one standard deviation, something like that. But what does that have to do with pi?
So you have to have a normalized distribution. So if you take the probability density and then integrate it from minus infinity to infinity, that has to be 1. And when you perform this, and what Misha was just explaining is that you typically do this by switching to polar coordinates, then there's one part of that integral that arises that gives you a factor of 2 pi, and that then gives rise to the pi and the normalization factor.
And it's very interesting that the Gaussian or normal distribution is surprisingly very common in nature. And one of the explanations is that where it comes from, like if you just take a dirty glass and use your finger to try to clean like a small circle, and that will be already a Gaussian distribution somehow.
Of what?
Like any hole you're gonna make, it's gonna be always since it's not perfect on the edges, it will always produce like a Gaussian distribution. If you try to send the light through the hole, if you like have a sash on let's say on the glass, and then clean up a small circle.
The blur on the edge of the circle.
Yeah, the blurring on the edges.
You're trying to connect it to the name of the podcast, like 632.
Yeah, I'm always thinking about
like
light.
Optics and stuff.
Exactly.
Okay. So basically that's kind of the joke that he starts out with, which honestly it is very suspicious that pi comes up all over. And so E and pi come up all the time.
Yeah. And also, here's very interesting. He talks about in the text that this point, like the first point in this joke, is that mathematical concepts turn up in entirely unexpected connections. So this is one of the magics of math, that you can have this pi in so many different things, but they come from different reasoning and thinking, solving different types of problems.
What about Wigner? Like, who was he?
Who's Wigner? That's a good question. I think who knows the most about this?
Well,
how do you pronounce his name?
Eugene Wigner?
How do you pronounce Wigner? Is he German?
Wigner, he studied, he's Hungarian.
He's Hungarian.
Yeah, so then he was a refugee during the Second World War, and then he came to the United States and worked on Manhattan Project.
Yeah, I think I've only really heard about him.
He worked on Manhattan Project.
I've only really heard
cool.
about him in the context of the Manhattan Project.
Cool.
And so he also famous in the area of quantum mechanics.
Yeah.
It says also that he was a very vivid mathematician. So, and he received Nobel Prize somewhere in 60s,
63.
3? Okay,
Yeah.
you know the right number.
That I remember.
For numerous, or like several contributions to the field of quantum mechanics, especially his Wigner's theorem on some symmetry. But, that's probably too deep to go today.
Cool. And I also want to add before we continue, he quoted like in the abstract, Bernard Russell, right? And I think that one of the philosophers and logicians that popularized the concept of math is beautiful, except maybe Einstein, is Russell. So I guess that's why he gave him a tribute. And yeah, another observation, there's no math in the paper, which is also nice. But okay, continue, Mike, about the next claims.
Well, I was going to go straight to my conclusion from reading the paper.
Yeah.
And we can go back to the kind of chronological, like what's really written in there. But I think the biggest suspicion I had reading the paper was that it's inevitable that the laws of physics are mathematical. Like I tried to think for the last 24 hours, which, Dan's been with me for part of that time, and he's been hearing me repeat this question. It's like,
At random times.
how do you just invent any world? It doesn't have to be this world, right? Any world, you come up with whatever physical laws you want that it cannot be mathematically described. And the problem is, if you come up with any law, the language, logic, syntax, like it's all actually very difficult to avoid having a mathematical description. So I didn't actually come up with anything. So even if you start, for example, you imagine you put your finger on a table and you press on the table, and instead of it pressing back proportionally, which is very mathematical, it pushes you back randomly. So it has a sometimes it pulls you, sometimes it pushes, sometimes nothing happens, random, whatever. That's very easy to describe mathematically, right? It would be like a distribution or some probability, right? So there'd be a probability of some value and so on. So it's very slippery. Anytime you come up with like a relationship, I try to think of like a relationship that's not mathematical,
So your claim is it's not surprising? Like you're not...
That's my suspicion. I'm a little bit suspicious that it's not surprising. Like it's obviously surprising when you, on the face of it, but then when you try to think of any natural law that wouldn't be mathematical, I mean, maybe it's surprising that the same math finds its way into different things, but then, you only have... It's the world is three-dimensional. Like it's kind of a boxed-in situation where, cyclical processes look like circles. It starts to like if you have a wave, it actually looks like a circle in a way, and so it's a little bit like... Anyway, so that's what I was very impressed with his arguments, but then afterwards, really thinking about it, I wonder if he's like just... It's an inevitability that he's surprised by, right? That there's actually no other way, because he doesn't give an example. He's not like, oh, but it could have been this way. He's just saying like, it's pretty awesome that it's like this, right? But he doesn't give a counter example, like it could have been different.
And it's also interesting that adding to this, the mathematical description of the world, that usually those expressions are not that sophisticated. Like even if you take the Newton's laws, it's just the first derivative of momentum equal to to the force acting, to all the forces acting on the object. So some of these things it's all like even Maxwell's equations. Can you imagine that all phenomena in electromagnetics can be described by Maxwell, like just four equations? That's it. Of course, they are maybe written in some differential or integral forms. Of course, you need a little bit of math, but in terms of the space, those equations are very simple and interrelated with each other. And they look really beautiful to me.
Okay, I wanted to say, I think that for me, the surprising part in general, not the paper, but the relationship between math and physics, is that there is any relationship at all, right? So again, there's math, as let's say it's some abstract concepts, and we won't go in if they're like real or not or where they exist, but there are like abstract stuff with infinite degrees of freedom, and we have like the physical world, whatever it is, and there's the mapping, like why even you can do this mapping. Of course, not every mathematical formulation you can map to our physical reality, but this mapping is surprising and beautiful, and I think one of the reasons scientists enjoy to a degree doing what they do. And often we don't think about it. We just take it for granted. And I would say that to what you've said, Mike, like as long as you have regularities in things, you can do the mapping from math to them, right? So if you can think of a world that has no regularities, maybe there'll be no math that can describe that. You get what I'm saying?
Yeah, but then...
So even random, you say, okay, randomly things appear, it's a regularity, so, right?
Yeah, I think almost it would have to be an illogical world. So I think the interesting thing is that, of course, our world is illogical because we can't explain where it came from.
That doesn't mean it's illogical.
It's kind of illogical, like because we can't explain any antecedent to the world that we exist in. If you ask, like, where did that come from, you're stuck. So it's definitely, in some sense, our world is also logical, but that's in a narrow sense, like in one little, there's just like one hole at the bottom or whatever. But in a very illogical world, you wouldn't be able to do math to predict what would happen. But then what's an illogical law, right? Like what would be a physical law that would be illogical? It's hard to come up with one.
But maybe to like go away from physics in biology, for instance, the law of natural selection, that may be one of the things that's quite difficult to capture, at least in its complexity mathematically. I'm sure people have devised models, but
yeah, they're like
that
imprecise.
is, yes, and basically the more complexity you have and the more you have a mixture of deterministic processes and then probabilistic processes, these laws may become emergent that are not easily describable by mathematics. But Russell's paper restricts itself to discussing the relationship of mathematics and physics, so he actually doesn't.
Russell's paper?
Wigner's paper. Wigner's paper.
With Russell's
Starting with
beginning,
Russell's quote in the beginning. Wigner's paper is specifically talking about the relationship between math and physics.
Yeah, so maybe biology. You're saying biology might.
Well, it's kind of I mean, there's a point in the book where he quotes Schrodinger's "What Is Life" about how it's a miracle that like humans can even understand the laws of physics and go through like all the logical steps. But I wonder if we cannot imagine laws of physics that are not mathematical because our brains are subject. Our brains are subject to the laws of physics, which are mathematical, right? So we can't imagine a world where it's not. That's one possibility.
I think that's a strong claim.
It seems like this paper should be also like extended to other sciences where, let's say, math and physics seems like have a special relationship. But it's interesting to ask like how it is good for describing biology or chemistry, where like, a lot of empirical laws. Well, of course they're connected to quantum mechanics, but it could be like very tedious to go through those computations, and sometimes you need to build special computers to get into this many body dynamics.
For chemistry and biology, should somebody write a paper like the uncanny ineffectiveness?
Maybe you should write that paper.
We need to invent some other language for describing those sciences.
So what I also find interesting is how Wigner concludes his essay, and it is by contemplating whether the success of the mathematical framework in physics is truly surprising, as we've just said, or if it might be a reflection of the physicist's inclination to use mathematics to describe the world. It might not necessarily point to a deeper truth about the universe. There could be other equally valid descriptions that we have not yet discovered, what we were just discussing. Those of you who may do quantum optics, which is probably not many, but this part actually reminds me of an excerpt from Ulf Leonhard's book, Measuring the Quantum Light, Quantum States of Light. And in the introduction, he actually muses about how quantum mechanics has been extremely successful in describing very diverse physical objects such as elementary particles, nuclei, atoms, light or semiconductor excitation, so right down Wigner's alley actually. But paradoxically, this universality may also mean that quantum mechanics describes our universal way of doing physics rather than the universe itself. So, however, the basic assumptions of quantum mechanics are not likely to be reduced to pure logic. They are indeed assumptions, and consequently they contain non-trivial information, not just about the physical world, but about us, about like how our mind interacts with that information. And that may be a clue to why there are similarities or why math works so well for...
Right. I didn't follow the logic.
Physics.
How was our mind connected here?
So he says that because quantum mechanics works so well, it may actually not be a reflection on quantum mechanics itself, but as how our mind is making sense of all kinds of different things, and it makes sense of various things, let's say math and ultimately physics, using a same kind of given process so that it sorts itself in the same way. So he's actually not going into the detail of this argument, he's just hinting at it. But I think someone who is actually talking more about this connection is Bernard Lonergan. So I had I think I had mentioned this before in our
I'm not familiar with
group
him,
chat.
but I'll check it out.
So he wrote a 800, 900-page tome called Insight, A Study in Human Understanding, where he...
Poem or tome?
Tome.
Oh, 800-page poem would be interesting.
Tome. He wrote a veritable tome that's called Insight, A Study in Human Understanding, which is kind of an extension to Hume and Kant, because he actually posits that the world around us is intelligible and we can arrive at actual knowledge. And the way he illustrates that is by explaining how math works and then explaining how the empirical method of physics and the natural sciences work. And he, in many, many more words, basically comes to the conclusion that we can grasp the world around us, but it is a dynamic...
We can or can?
We can.
Ah, okay. Oh, okay. Now I feel safe.
Including, yes, right, because we're all scientists, so including subtle comments on cause and effect, that any kind of understanding we may arrive at by following a certain process that is already installed in our
But that's physics,
hardware.
right?
So
We follow a process and we get something, right? Not anything, but...
Yes, exactly. And to physicists, it's very natural, but you actually use the same process in common sense. Like, it's actually the same process which is not codified in math, but for instance, when you see a riddle, you kind of, especially, these IQ tests where you see a riddle, there's like a sequence of numbers.
And then the next one, yeah.
And then there's a moment, so you muse about it, then there's a moment where you're like, I got this. But then you test it by writing the next number in the sequence. And then the person administering the test tells you whether you're right or wrong. So even in like a non-scientific context, there are these things where we see patterns and then we make a prediction about that next thing. But the way we form these laws or patterns, that's, according to Lonergan, that's something that's like consciousness that's already, that we are equipped with, that's separate from the empirical world we're perceiving. So I really recommend reading that as an extension to Hume, yeah.
So reading 800 pages.
Motivation to do that. Shall we maybe come back to like text? What since he talks about at the beginning about like maths, what is mathematics, what is physics, he gives his opinion. I don't know, was there anything striking you found? Any insightful? Like, I don't know, from the physics part?
I agreed with the physics, like how he defined physics. Not sure I agreed with how he defined math.
Yeah, because he has an emphasis on the invention of concepts, that it's a creative, expandable thing.
Yeah, in physics he gives like example of, essentially he says that the physicist is interested in discovering the laws of inanimate nature. In order to understand this statement, it's necessary to analyze the concept's laws of nature. And then he gives an example of the Galileo, the Italian guy who in 17th century was throwing rocks from the tower.
Dropping rocks very carefully. If you throw them, it doesn't work. I don't know. Releasing rocks.
Them carefully.
Otherwise, they can land a different time. And then surprisingly, it's interesting that if you like repeat the same experiment in different places, not specifically in Pisa or at any other tower or with other different types of objects, they would land at the same time if you release them simultaneously. And those laws of nature, they are actually like not changing.
So there's invariance. Yeah, that's an important concept.
Independent of like size, material, shape, and body.
It's so
Which
inclusive.
is surprising. The invariance is surprising. Doesn't have to be that way, for sure.
Yes, exactly.
That's not a given.
Yes.
Yeah, but you need it in order to get regularities.
But you could have a monotonically changing. For example, from one side of the universe to the other, you could just have a changing set of rules, like monotonically, for example. Like the force of gravity just increases as you go from like the center of the universe to the edge.
But that would not necessarily change. That would not change the form of the laws. That would just
So
change the constant.
it's still regularity.
There's also something else weird, which is that the forces the rules are orthogonal. So like gravity is like if you apply an electromagnetic field, let's say you apply an electric field to something, its mass doesn't, its gravity force doesn't change, right? Why? Like there's no reason that the laws couldn't interact with each other, but they don't also, which is strange.
They're written in a certain way.
Yeah, there's like
Someone designed
it's like they're orthogonal basis vectors or whatever. Like they're completely unrelated in some kind of space or whatever, right? Yeah. Like they could affect each other, but not.
Maybe it's just done so we can, separate them, can grasp the understanding. Otherwise, if it's all will be messed up, like we need some, AI, but we need to get it.
But in the end, theoretical physicists aim to unify all of the fundamental laws of physics, including gravity and quantum electrodynamics.
If it's one law, but it's odd that they don't seem to affect each other. I mean, you could imagine that if you have like an evolving system, right? This is what people used to think about biological stuff, that it was like intelligently designed because it's so amazing, works so. So it could be that everything is fine-tuned by evolution. So the laws evolve over time, and then you end up in the universe where they're reasonable.
Yeah, I
right?
mean, that's
and
what is usually called the anthropic principle. Given that we exist, everything
and so
had to line
in this
up.
universe, they're orthogonal, because if they weren't orthogonal, it would be impossible to survive. You'd be going from place to place, and like with small changes in electric field, you would have a change in gravity, you'd get crushed, this kind of thing, right? Like you can imagine.
So it's like a Goldilocks of all of the different
like if they're not
parameters and
orthogonal,
laws.
you lose the Goldilocks situation or something.
Yeah, and it's related to the fine-tuning of all the constants of all the...
Yeah, not only are
theories.
not only are the constants fine-tuned, also the laws are like tuned up to not have any relationship with each other or something.
And so predictability, what we talk about is, or like the laws are not changing, at least not on the visible scale. So that helps us to build like machines or, things like nuclear reactor. That would be a disaster if you design it for one parameters and then
you put it
the next day
in a different country, and you have to redesign everything.
I mean, there's the theory that dark matter is actually gravity changing, right? I don't remember whose theory this is, but it's like, I think it's a contrarian Israeli guy also. Just like all the contrarian theories,
I heard about
all the
it.
great contrarian theories come from Israelis.
He says like you need actually to change the...
I think it's literally the constant. If you just adjust the gravitational constant, you can.
Something basic. He says you need to adjust something basic. I don't remember, but I heard about it. I think it's from like Weizmann Institute.
There's a thing that I like to joke about, which is that like, if there's a vacuum of disagreements, it'll always be filled by an Israeli scientist. There's like a guy in Israel who's also, his whole thing is like that quantum computers will never work. So that's like, there's a guy like that. And then there's Avi Loeb at Harvard, who argues that the Oumuamua was a alien spaceship. So that's like a very useful activity, to disagree, right?
It's like moving against the trend, the main trend.
Yeah. They're like
someone needs to do it.
They fill the vacuum of contrarian like positions. If there's ever like a good contrarian, like a little hilltop that you can defend as a contrarian, if no one's there, you'll get an Israeli there.
I think the guy you're referring to is Milgrom, who came up with Mond. Mond is German for moon. It's modified Newtonian dynamics, and then he's developing that. But
is he actually Israeli, or is that just a bad guess?
I don't know.
I heard about somebody from Weizmann Institute.
Okay.
Yeah, for sure. Maybe somebody else who's trying to tackle it.
Another thing I was thinking when I was reading this, or maybe at some point after reading the paper, is like if you psychoanalyze these guys, like when I studied quantum mechanics, it made me I was like, they just made it up. Like they just started taking some classical equations, applying, a little bit of like a couple tricks to it. Like the worst one for me was, there was at some point in some class where the teacher said, okay, and then we take the equation for an orbit for a planet, and it's literally like a classical normal mechanical equation. and we're going to turn it into, we're going to use an operator here, right?
We're going to quantize it.
And we're going to quantize it, whatever. And then they're like, I'm like, well, why do you do this? Like, why did they do this? And she basically said, like, look, they just tried this and it worked, And I think these guys felt a little bit guilty. They're like, okay, we tried all this stuff and it just worked out. We don't know why it worked.
It was motivated by paradoxes that couldn't be solved.
No, of course. There are reasons that they tried this. I'm just saying that they weren't trying it with like there's no real way you can argue that taking the orbit of a planet, taking the equations that govern that, and just quantizing them and throwing some operators on top.
But that's not historically how quantum mechanics was developed, so that may just be how they presented it in that class, because historically there's like the UV catastrophe and the back body radiation.
But the Bohr's atom model, I think it was originally, they proposed like several ways how, let's say, the particles, they knew that there is some positive and negative particles, but they didn't know how they align.
So Bohr's atom model kind of makes sense for it to be an orbit because it's like negative orbiting around positive. But once you start doing Schrodinger's equation, that stuff all falls out, right? So why are you still using the orbit?
The Bohr's model is actually it still can predict pretty well like the experiments on the spectrum of the atoms, like about the lines. So they were able to put that knowledge and find that those lines are discrete, and they were like, okay, maybe those orbitals, the transitions are.
But he wrote about it in the paper in the. He said that the matrix formulation. Of quantum mechanics, they just, said, okay, let's try something. It looked good, and then they tried on other things, and it worked. So it was just like, somebody tried it. I remember he said that he quoted the name. So,
but you see, there is also the for the quantum or like atomic physics, there was a problem that it started from Bohr's model. And then they would jump into more sophisticated things, like, as you said, matrices, the density matrix analysis. But they couldn't move too far with analytical calculations, so they got stuck on helium. They could solve hydrogen, helium, but it's almost like impossible to analytically calculate all the other atoms. So that's why in chemistry, a lot of things is just like empirical. Like most of the reactions, you can't just write them on the paper. You have to use some approximations around these crazy simulations.
But it's definitely, at least it feels to me like in a way, there's an insecurity. Like when he writes the paper, like, why is this working? It's like a suspicion. Is it because we're so excited about math and we're missing something? Like he says, what if there's a whole different theory that also fits this, right? And so on. So there's certainly like a feeling, which probably people didn't have. Like, I don't think Newton felt this way. Maybe he did, actually. I don't know. Like,
look, he worked, differential equations, whatever he was working back in the day, in limits and stuff.
And suddenly it also...
No, but also those concepts are quite abstract.
Yeah,
so
I wonder.
Newton also was surprised, but he was extremely religious. So who knows what? God
if you're
it.
religious, it actually makes it much less stressful. That if you're religious, it's not stressful that math is like describing everything. Because
that's why when people are surprised that religious people could be amazing scientists, they say, "Oh, like this is contradiction." In my opinion, no. It's like orthogonal views about different questions, and actually maybe
it actually resolves a lot of the anxiety, right? Like it's like, why is this working? Whatever.
If you do biology, it's so surprising. It's easier to.
Should there be like a meme of Moses coming with the two, stones, and there isn't like Newton's equation,
and then
like
he
quantum
drops
mechanics,
them from the Tower of Pisa,
and then the Maxwell equations. But he puts different statements, and then he'd be like, well, how would I explain all the other laws to people with their background at that time? I have to simplify all the science.
Start with the Ten Commandments, and
10
only
Commandments.
2,000 years later, you get the rest.
Actually, I thought something related to what you said about the anthropic principle, like how everything is fine-tuned. Because, we are here, so it couldn't have been otherwise. So maybe it's related to the paper in a sense, like why it works, because we are part of the world, and whatever mathematics are, we use it, right? So it couldn't be otherwise, because we are somehow part of it, or it's part of us, and we're trying to understand everything. So it's also some kind of entropic principle plays a part here.
But show of hands, do you think that mathematics is given? It's part of our universe, or is it something that humans invented? What do you think? You first, Mike.
It's not the same. If it's something we invented, it's part of the
Yeah,
universe.
is mathematics just given? Like, would it still be
No,
there?
invented.
If we...
I think it's given, because invented is like, for example, the iPhone is invented. Like it didn't. You can have a situation with no iPhone, right? It's not like a platonic form that exists somewhere. It's for sure there. Yeah,
that's exactly
it's there
it.
for sure.
You
It
think
exists,
of it as a platonic form.
I would say it exists before anything else, right? But I think before we can vote, but before I just want to respond to Dan. I think like, okay, maybe the types of math that we can discover, like as mathematicians, are in some ways baked into our brains, right? Because the brain can only do certain operations, right?
Exactly.
So maybe there are certain kinds of math that actually we can't do because the operations just don't, they just don't cook in your head, right? Like you can't, no matter how you put together, whatever, because he mentions this in the paper, like how can you string together 1,000 steps in your brain? It's crazy, right? That you can even perceive, because some of these things are extremely difficult to even pay attention to the entire flow, like the entire argument.
Like Fermat's the proof of the principle of what's the
Fermat's last theorem.
Yeah, like it's crazy. Only 5 people in the world can follow it, right?
But yeah, for the brain, it's also interesting that when we walk, there's like so many information passes through us, like which force you need to apply there. There's like, seems like a lot of computations are happening behind the scenes, but then somehow we're quite restricted in terms of like calculating matrices, like multiplying vector with matrices.
Yeah, like if you want a robot to perform those motions, you have to do, it's what Azar was talking about, the special matrices, the
rotation.
No, but it's with an L.
Lagrange?
Lie group.
Lie group. Yeah.
But for robotics, it's usually quaternions. That's rotation in 3 dimensions. Because complex numbers are rotation in 2.
Yeah, but for some reason he was saying that the Lie group is like whatever. He does robotics, but anyway,
it's like Pauli matrices is the Lie group.
For sure, you're not. But maybe as an analog computer, you're just performing those calculations, but you don't have it in memory. It's like analog, right?
I don't think we perform calculation, but that's a different podcast episode.
It's more like maybe it's I don't know. Have you thought in general like how the math even appeared? Like how did it? I would understand when people start like maybe trading. They would be like, okay, I have how many I don't know pieces of bread trading for some fish, so they could start calculating based on their fingers, and then maybe there were some astronomers of that time looking at the stars, trying to compute some trajectories. I don't know. What do you think? How did math even start to appear in our society?
I think similar to language. It's not so different. Math is a type of a language.
Who was the first mathematician? Some of the Greeks?
Yeah, the Greeks, they had some...
So before Greeks, no one really thought about that?
No, everybody had like, the Egyptians for sure had something, and the Mayans had like all kinds of astronomy. But I don't know if it's math exactly.
I think
like
it was...
Where do you call math?
In Greek, was it the land dividing, like the Pythagore and Euclidean geometry? Yes. They were like trying to be fair in terms of how they sell their... pieces of land.
Yeah, like calculating areas and stuff.
This is where
it's
the
a good
pie
question.
came.
Was the first? Yeah, I guess the claim would for sure be like some trading thing, right? Like you're trying to keep track of some
quantities,
right? Quantities become very useful.
So you get quantum.
Was it the stars where was the first connection between the mathematics and physics?
No, I don't think so. I mean, even earlier.
Geometry.
Like Kepler?
Geometry.
No, geometry is math. But where does the physics...
It's connected.
What was the
like
first
levers or something?
But even Pythagoras, like he had the monochord and then he was dividing the
monochord
like into different ratios.
It's in the physical world. They used geometry to solve problem in the physical world. That's exactly math and physics.
No, I mean in terms of like physical laws, like Newton's laws, or like Kepler's, how the planets move, like gravitational laws.
As far as I know, it's around Galilei. Maybe,
Galileo,
what's
17th
his name?
century. Seems like there was some breakthrough at that time. So it was pretty silent, and then there was a spike in terms of, we have a...
Did the Greeks Greeks discovered 0 physical laws? Is that true?
No,
That
that's
might
not
be
true. Like
Maybe 0. They had some
Well,
math, but-
Archimedes.
Archimedes, yeah.
buoyancy.
Is that a physical law though?
Yeah.
Not really.
It's not like gravity, or it's not fundamental, right? I mean, that's more like a know-how or something.
So who's the father of gravity? Newton?
But yeah, that's probably the closest.
Newton? When the apple dropped?
I don't know if there was ever an apple actually, right? It's not. that's
Oh,
not
is
supposed to be
the
right.
story
I mean,
tale?
maybe, yeah, I don't know.
I think modern science, like, dates back to around Galileo, right? And I think he was the one that also talked about like philosophy of science, saying, okay, there's the mental stuff or subjective, and there's the objective world, and we can use math to try to understand the physical world. That, I think, was Galileo Galilei. Like, that was, if you talk about modern science, usually that's when they teach philosophy of science.
So this is the starting point?
The official story of like history of science is that the Greeks were like just coming up with stuff, but they didn't care about experiments. That's the official story. Like certainly Aristotle was accused of this, that like he would just come up with theories. Some of them were right, some of them not. Like he'd have theories about anatomy, right? He'd be like, this is what is inside an animal, and he just wouldn't cut open an animal to check. He would just
There's the four
write up
elements,
like a...
and each element wants to go back
Yeah,
to,
stuff like
to where
that.
it belongs, right? That's why like air goes up in the water because it wants to go
Yeah,
back
just
to where
make
it
stuff
belongs.
up, and then sometimes it was actually very insightful, but they wouldn't do experiments, so they had no way to
but
like really...
There was one Greek
climb the ladder.
philosopher / astronomer who was able to predict a solar eclipse that brought him to Thales. Or I don't know how you pronounce
Thales,
it.
yep.
Thales, yeah.
And geometry.
Yes,
the Thales rule.
exactly. So he was known to dabble
Was that
with
experimental? I guess he
geometry.
predicted, and yeah, that's sort of
I
experimental.
think it's not really known how he did it, but he must have observed the movement of celestial bodies and had some hypothesis around why there should be a solar eclipse at that particular time. So that's his claim to fame.
And also, what do you think now? What is happening? Is it everything solved already? Like, all the...
Wait, does math exist? Wait, but first, does math exist?
Does math exist?
I answered the question, but I don't think you guys answered, right? Does math exist? What was the
Independently of humans.
Yeah,
Independently of humans.
independently of somebody thinking of it. Like, does it exist before you think about it? Like, did Hilbert spaces exist before Hilbert?
And it's
I mean,
just like
apparently,
this
yes.
perfect form. It's just perfect.
What about before the universe?
That's a very good question.
Before the
Does
universe?
math exist before the universe, or do you need the universe to have math?
Yeah, of course you do need the universe. I think universe comes with its laws. That's my philosophy. I mean, we're going to like philosophical
If you
questions.
change the universe...
Metaphysics, yes. But
No,
that's
but
okay.
imagine any universe, you still get the same math. You can't change math by changing the universe. You see what I'm saying? Like you can't change the a squared plus b squared equals c squared in a way.
I mean, it can be. If it depends who
You can imagine a different universe with different laws, right? At least that.
who renders this world. I mean, that's my vision. So someone coded all their laws, and they're like, okay, hit the enter button, and then here we go. Here's the product.
My answer is I'm a monist, so there's only one thing metaphysically. So I would say, yeah, the universe comes with math. It's together. It's one thing.
You get it at the same time.
Yeah, at the same time. And every distinction we do, there's math, there's physics, there's mind, there's matter, all of those distinctions we do, it's just our perspective on this one thing that it exists, and that's it.
And it's so beautiful also.
Yeah, and it's beautiful. That's without going deep in the rabbit hole. So it's together.
Yeah, I don't think you can create beauty by random process.
Math exists or no? What's your take?
Yeah, I think it's
You asked the
independent.
question.
It's independent.
Independent?
It's there, and we discover it, at least in its form that we know it, in this universe.
But imagine
there.
a different universe. How would that change math? Like, would that change math?
It would.
It's a serious question.
I mean, it depends.
It would change the mapping. So in
Yeah.
a different universe, there'll be a different mapping between all the possible
Different constants.
states of math to that particular
Human
universe.
geometry, it's not necessarily on
But
the
let's
plane.
let's just take simple math, like just multiplication. We don't have to go into like anything else really. If you take simple math, what can you change about the universe to make multiplication different? I mean, there's not, because it lives on its own. It's completely abstract. Like maybe multiplication doesn't apply to this universe, but it doesn't get rid of multiplication.
No, why? You can imagine multiplication when the output of multiplying two numbers is another two numbers. It's not one number. Or whatever. You know, you can go crazy. That's
What
a
about
different...
a universe?
But would that still be multiplication?
What kind of multiplication are you talking about? It's like simple multiplication of vectors, of tensors?
I mean, just A times B is C.
Well,
like just numbers.
well, that
just
one
counting literally like fingers.
Well,
you know?
this one is just, you just agree that 2 by 2 is 4, right?
Yeah, you assume
it's an
multiplication
axiom.
is defined abstractly, right? So like if you define it, for example, in this universe, you know, the useful version of multiplication is like A times B is C, right? Just for numbers, you know, 4 times 4 is 16. But like
Which base?
yeah. But yeah, my point is just if you pick whatever abstract mathematics, I don't think if you need to. You see what I'm saying, right? Like these things exist independently.
But what
like
if
whether or not it maps to the universe you're in doesn't change because you could imagine a different math that doesn't map, and that math would exists, right? Like
Different
it's
type of
not.
math. I mean, we can just create a new type of math.
what
Yeah,
if
yeah, exactly.
discrete objects didn't exist? What if you had a universe where everything was continuous? Would anyone ever, like some intelligent thing, consciousness, ever come up with the concept of numbers if everything was just a continuous blob, like there's one consciousness, continuous blob that is the universe itself and thinks about itself? Would it come up with numbers? Probably not, if it's just a thing.
That's true. That's true. We were also talking before this about like what about a universe where everything is infinitely big? So each object is infinitely large.
Yeah.
And they're somehow all there. You know?
Doesn't mean anything to me.
So maybe math is connected to the specific universe we are in and how we make sense of things. I don't know.
And I feel like it's also interesting that there are like specific numbers which appear too often in many different areas, like the normal distribution, the circumference of the...
Yeah, E pi.
Where else we can maybe count? Where do we see pies and how many things?
Square root of 2.
I feel like E I'm actually comfortable with.
E?
Because E I kind of understand why it shows.
Dude, do you know what is it?
It's the number where its own e to the x, its own derivative is e to the x.
No. I like the explanation. You take one and
It's
then
a
you
limit.
multiply one infinite number of times.
It's
and
a limit.
And you get the E number.
E is a limit.
It's a limit, yeah, exactly.
it's
That's
a
what
limit.
I'm saying. It's
Yeah,
like
yeah.
1 plus 1 over
One
n to the power of n,
yeah,
and
it's a
10 to
limit.
infinity.
Yeah.
But isn't it amazing? You just take 1, multiply infinite times, and you get 2.71, blah, blah, blah. It's magic to me.
And limits, like infinity does not
It's
exist.
supposed to be 1, right? If you take 1 and keep multiplying by 1.
It's like the Riemann zeta function, get minus 1 over 12.
Yeah.
Yeah, but I think E is not that suspicious because it's e to the x is when you take the derivative, you get e to the x.
Yeah,
so
yeah,
that's a special number.
that's-
that should show up in a lot of places because it's like this sweet spot, you know, which must be like. You see what I'm saying? Like it's kind of a. Whereas pi, doesn't even. I guess pi is half a rotation, or whatever. It's like,
Well, for trigonometric functions, like.
so basically anything cyclical.
But when you have E and then like 2 pi, so that's exactly like the full circle of the phase. Then we get to these complex numbers. I mean, that's an interesting example
he talked about
where we
complex
went
numbers.
beyond, the math which describes the physical space into our like real and imaginary things. And it's interesting that it helps to do the calculations in that complex space and then come back.
And you need to come back.
Or like in quantum space, everything is, is complex. It's Hilbert space with
And
complex
also without.
amplitudes.
I mean, even electrical
engineering,
so much
everything.
But in
easier.
electrical engineering,
Fourier
you always come
transforms and-
back. You always come back to the real.
Yeah, but also in quantum mechanics.
No.
You need to take this. If you want to do the square, to square of your amplitude to
But
get.
then there is a phase thing. So phase, you can do measurements on interference type of measurements, where this imaginary part, like that favorite Michael's number E, with the Ix would appear.
But still, you take the real part.
Oh, but yeah, it will. You will take the real part, but that imaginary part will play a role in that.
Yeah, of course, it plays a role. Also in electrical engineering, like it's supposed to be the inductor or whatever if you're ROC circuit.
But do you know why they introduced in electrical? Because again, as Michael said, the beautiful properties of the exponential function, because its derivative and integral are easy to calculate. So you go to the real imaginary space, do the calculations, and then come back instead of dealing with these nasty cosines and sines and whatnot.
By the way, related, I asked before ChatGPT, I looked into, can you formulate quantum mechanics without imaginary numbers? Mm-hmm. Okay, the answer is yes, you can do it. And actually, there was a paper in Nature by Gisin, Gisin, Nicolas Gisin, I think it's Gisin or Gisin, is French physicist. And he claims that this formulation actually will show different empirical outcomes. So it's actually testable. So it's like a different formulation of quantum mechanics, he published in there. So it's really interesting, this question. But yeah, maybe we're digressing, and we should continue to the last paragraph. I think it's a cool one. Yeah, we should read it out loud
maybe
for
before
everyone.
the last paragraph, I think there is another interesting thing I want to point out about like uniqueness of the mathematical models for physics. So he says we're in position similar to that of a man who was provided with a bunch of keys and who, having to open several doors in succession, always hit on the right key on the first or second trial. He became skeptical concerning the uniqueness of the coordination between keys and doors. So it's interesting that the doors of physics can be still opened with different types of keys, like some of them are more precise, but in another case you can still have like rough like bar model, say for quantum mechanics, and you don't have to go into like, for example, density matrices to do the calculations. So it's interesting that there are like several approaches, like even for gravitational for the gravitational physics, like, you know, it started from Newton's laws, like, which are very simplistic, and then it expanded by Einstein, who came up with this general theory of relativity. So maybe there are even more things which could, you know,
it shows that
more sophisticated.
Yeah,
and more.
that's why I'm quite skeptical of unifying everything into one theory.
But also that next thing that we may need to describe a new phenomenon may still pass as math. So for instance, going from classical mechanics to quantum mechanics, you go from calculus to probability theory. So those are different parts of math still. So we don't say that probability theory is a different type of language. It's something new, a new tool that we invented. So whatever else we may invent, probably we would call math as well. Could be one answer to that. It would have to be something wildly different that cannot be classified as math.
I mean, the interesting question is, like, why did it really have to, like, okay, quantum physics especially, they were just, again, at the beginning, there were some clues, like, okay, something's wrong. When you heat up a metal, it's putting out the wrong wavelengths and so on. But in the end, they're trying different ways, you know, making stuff up, or almost making things up, like taking analogies and using math to check if it'll be predictive. And the question is, like, if they tried this 300 years earlier, before some of that math was invented, like, would they have solved the problem? Or did they literally have to wait for the math to, or not invented, found, whatever. Before this math was found, would they have solved the problem some other way? Or did it literally require some of that math to be found before they could, you know, why? So basically, if physics was ahead of math a little bit, would it have to wait for math? Or, like, what would have happened?
Not always. Like in Heisenberg's case, he reinvented matrix multiplication independently of math. So that had already been around, but wasn't really used by
Oh, I see.
physicists.
So he wasn't. He later it turned out okay. This was already mathematicians were doing
exactly.
this.
So he
I see,
just
I
wrote
see.
down tables and made up rules for how these tables needed to be
Yeah.
multiplied or combined. But it turns out that those rules were actually matrices and matrix multiplication. So he
Literally matrix multiplication.
Yes. So he reinvented.
This is the matrix mechanics.
Yes. So he reinvented that. Yeah.
It's amazing. We're still surfing on those matrix multiplications into the new age. So that's what I was asking. I would like to repeat again. So what do you think? Are we done with math and physics? Is everything discovered, or do you think there is a way that maybe AI could help us, to get more theories and maybe help to unify the unmatchable, unstitchable theories like general relativity and quantum
So I'll
mechanics?
tell my view. So again, if there's like the physical world, then it's something. And there is mathematical world, and there's infinite degrees of freedom there, right? That's why we had some more, less sophisticated theory, and then we found a better theory, etc. So my view is, if an algorithm can search, right? So this mathematical world is infinite to a degree. It can do better search there than we are doing as a human species. So maybe it could find better theories, or not theories, like formulations. Because to me, it's a mapping. There's the physical world, there's the mathematical world, and we try to find better mappings that work better, in a sense, give better predictions. So in my opinion, for sure, if you can automate this search, the scientific process is to search this mathematical world for better formulations, maybe it could help.
I think there are clearly still things that need to be discovered. Like there are inconsistencies. We don't know what dark matter is, so that's a very...
We still didn't give in on dark matter.
It's a
Trying to figure out what is it.
Very good hint that there's something missing in the picture. But then also what I said earlier, we don't know what consciousness is. Like there's definitely topics that
Where life
are
comes from.
Origins of life, consciousness, for
unexplored,
sure,
yes.
I don't know if consciousness is even a scientific. In my opinion, it's not a scientific question, but...
I mean, maybe like theoretical, if you think about it, if you're like investing, right? So what would you invest in if you wanted more physics to happen?
Shrooms.
Actually, I don't think that's a wrong. I think that's a good.
It's the best answer,
This is how we get to the changed state of mind and...
The stoned physicist theory. You know the stoned ape theory?
No,
that's
what's
like
the stoned ape theory?
It's very popular
on Netflix
amongst like, degenerates, but it's basically like
Joe Rogan.
Yeah, it's basically like the stoned ape theory is that humans were just near maybe getting intelligent, but not quite, and they were that way for a very long time. And then some human tried, ate some bad mushrooms like growing on cow poop or whatever.
No, you say they ate a lot, not just one
Antelope
time.
poop or whatever. But they kept
a lot of times.
They were just getting slightly up leveled up or whatever by taking these shrooms, right? And somehow that led. See, this part I don't understand in the theory, but somehow that led to an evolution of more intelligent people. So basically, like it was sampling the space of like what would happen if people were more open-minded or more intelligent or whatever, because they were maybe slightly below, like they had low creativity, let's say, but then they would sometimes like eat these mushrooms, get poisoned, become more creative, and maybe like make a tool or something.
But how would that pass
then
down
eventually,
genetically?
It wouldn't, but maybe it would like somehow select for more creative monkeys somehow. This I don't think I'm a good...
I can answer.
You can answer
No,
this.
like we
Okay.
talked about this today in a different...
You talked about a lot today.
Oh, but let's say you need like to jump like a potential, right? You have like a potential wall, and you need a lot of energy to go over it. So in a sense, if like a lot of humans are creative at some degree, few of them will take whatever psychedelics, and then maybe they can jump so then maybe they can invent something.
But
that
the question is,
wasn't
how
there.
does that pass to the next generation? That's
Maybe the
part.
tools pass. I don't know.
Yeah, and then maybe the ones that can use them get selected.
Yeah,
and
whatever.
things
So
like
it maybe
that.
not just like IQ-wise, just some kind of
I mean,
jumps.
you could argue that you've seen this with coffee. Like when Europe discovered coffee, things just started happening. They switched from beer to coffee, and like
Is there a clear demonstrated correlation?
Yeah. For sure, like the French Revolution and all these things, or at least. So what happened is there were
First time I'm hearing about this.
So England was when England started trading and getting coffee. I think this is in the 15. Yeah, maybe this was tea in England. But yeah, caffeine. So basically, you couldn't drink water because it would be like you would get sick.
Oh, so you say switching from beer.
Yeah, so beer is one way to
tea.
sterilize water. Another way is to boil it, and so people would sit in coffee houses or tea houses and drink a lot of tea, and this would make them more excited to talk and so on, versus coffee, which would. There's actually there's a lot of memes that are like, this is what the alcoholic societies, the psychedelic societies, the coffee. I mean, we live now, I would say, in like a coffee society.
Yeah, we are a coffee
where
society.
everybody is programmed by coffee every day to like sit and like.
Well, now we're trying to deprogram it with decaf.
Yeah. With decaf, we're trying to we're getting deprogrammed.
We're just sliding down.
But like maybe like America in the middle of the century, America was like a nicotine society, right? Like everybody, the room where like they designed the Apollo rocket or whatever was like full of smoke. Everybody's smoking. Anyway, yeah. I'm not suggesting anything, but okay. But the thing I wanted to say earlier was actually very interesting, but we got off onto the stoned ape thing.
Somebody shouted shrooms randomly and derailed the conversation.
What was the thing that we can cut this, but what were we talking about before the shrooms?
Don't cut anything, Mike. Come on.
If there is any like future, where are we going with?
Yes. I was saying, if I was investing, like if I put on like an investing hat, and I said, okay, I'm going to invest resources in finding new laws of physics, right? Maybe you just cut out the theoretical physicists for a while. They're clearly not having a lot of success, right? So you remove the middleman. You just have experiments. You have the experimentalists and the mathematicians, right? And so you just produce more math and produce more experimental data.
They would never be able to communicate.
Like it might, but they don't need to communicate. You just do that for a century, and then, or 50 years or a century, and you just produce as much math as possible. It doesn't need to be applicable to anything, and you produce as much experimental data as you can. Improve your equipment. Get better,
just
whatever.
Take
like
measurements of
neutrino
things.
detectors.
And then it's a search problem.
You just try to get a better measurement of what's going on, improve the equipment, etc.
Gold diggers.
Take more precise measurements of a quantum phenomenon. Build more quantum computers. These kinds of things.
That's literally what I'm doing.
Astronomical better observatories. Like just collect more data. Giant interferometers, whatever. Right? There's lots of ideas. Right? Like build more colliders or benchtop quantum experiments, whatever. But don't try to make any theories. And then you just invest everything in them. Take all the experimental physicists, just make them do math. Like forget physics, just produce more math, right? And then maybe in like 50 to 100 years, you've built up enough math that like something starts to fit the experiments. You see what I mean?
Yeah, I see what you mean. Yeah, that theoretical physics basically is not helpful in this context.
No, it depends. But if you have more math, you're just more likely. I mean, this is what Dan was saying. Like if you just have infinite math, you're more likely to find something that has
it's
a fit.
a search problem. You need to search for an infinite space.
Physics to get stuck in the Stone Age and then the math.
But I feel like theoretical
skyrocketing.
physics to some degree is at that stage because a lot of theoretical physics is not falsifiable. The theories that are produced are closer to pure math.
But maybe the problem with string theory is that they're actually still trying to do physics. Like they should just say there's no application. Like this is pure math, we're just playing. And then it would free them up to do more, there could be
more
many
crazy,
more. Or just many, maybe like string theory is crazy, but maybe you could think of 100 string theories pretty quickly if they didn't have to match to anything, right? Like, it's like, but anyway, it's just, just as looking at it as an outsider, like I'm not a physicist, you could start, based on this paper, you could start wondering like whether you just need more math, right?
I think we need a mathematician here to tell us what's going on.
Oh, mathematician would tell you always need more math.
No, actually, often they're not like pragmatic. They don't care if anyone needs it. They just enjoy doing it because it's beautiful, and it's like intellectually fun.
Right, it's relatively low cost to produce math. Like, it's just pen and paper.
What has happened now in math? Like, what are they?
No idea.
I mean, I have seen that they could solve some like Fermat problems. It's maybe like a challenge, but how is it related to ongoing things? in other sciences.
No, it's not. I mean, but like neither is. I mean, complex numbers or whatever weren't immediately applicable. I don't think. So just if they could produce another hit like complex numbers,
Another hit.
that would be a big.
If mathematicians, maybe you need to give shrooms to mathematicians.
They're already. They don't need any more shrooms. Not the ones I know. Not the mathematicians I know. I think don't need it. Okay.
So Michael, how do you invest in that?
How do you invest in it? I guess if you're like a grant agency, I don't know who's working on making new laws of physics, like NSF.
Yes,
I don't know.
yeah.
You know,
For
I think they're
example?
more like experimental. They're trying to do like more applications. I think that's what is probably killing the academia, because
it's
they
very
try to mimic
applications
like
focused. Yeah,
applications is everywhere. Like in every paper you need to write, why is it useful?
So Vladimir Arnold actually has several interesting quips about this. So to your point, for instance, he says that there is no applied sciences, like either it's engineering or it's science. There's no such thing. There's no such thing as an applied science. But also, like in general about mathematics, he actually thinks it's a part of physics. So he actually, the quote is, mathematics is a part of physics. Physics is an experimental science, a part of natural sciences. Mathematics is the part of physics where experiments are cheap. This is where what you were just saying, yeah.
So by the way, this brings up an amazing thing about this paper. There's not a single word of like trying to justify this for like benefit to society, like nothing. You know, there's nothing in the beginning that says, well, you know, there's so many problems in the world. We don't have enough energy. We have too much this. You know, we need to discover
The healthcare system in Madagascar.
Exactly, the
Just go
healthcare
directly to the
system.
point.
No, there's nothing. He doesn't try to justify, even though he doesn't try to justify anything, which is amazing. Like now, if he wrote this paper today, he would be thinking like about his next NSF grant, and he'd be saying like, well, you know, physics has benefited society in all these ways. Like we've built, nuclear energy and, you know, medicine and, you know, whatever, right? Like he'd be saying MRI, you know, he would write a whole paragraph, like, think about it, like math gave us MRI, you know, he would have to justify it all. But actually here, I don't think there's a single justification of any benefit to anyone.
I mean, he mentions nuclear.
The aesthetics, like it's beautiful.
Exactly, yeah. He literally says it's just nice.
It's beautiful, like it's subjective.
Which is
for
very
the-
honest, you know. I think now physicists feel the same way, but they're like, I guess, you know.
It depends.
It depends on the person, but I think a lot of people feel this way, but you don't see papers written this way much.
But you see also, Xinhui said it's an essay. So maybe that's why we should need to come back to write an essay instead of writing.
Yeah,
journal
no, people
articles.
should do that. And I really enjoy Arnold's writing, but this is also from like some decades ago. Vladimir Arnold, he has some more like really funny quips. He wrote a really good book on classical dynamics, that on mathematical classical dynamics. It's quite great. But he also wrote a lot about math education, and so he also has this quote that I really like. Or it's funny. All mathematics is divided into 3 parts: cryptography, paid for by CIA, KGB, and the likes; hydrodynamics, supported by manufacturers of atomic submarines; and celestial mechanics, financed by military and other institutions dealing with missiles, such as NASA. It's like his take on how math is like divvied up.
It all depends on your sponsors. So be careful.
But also
So who's sponsoring this?
Sci-Fox, but also
Well, on donations, personal.
Unfortunately or fortunately, the barrier to entry to making podcasts has gotten very low. So it's not, there's no, you don't need a publisher.
But Arnold, interestingly, was against the notion of being guided by beauty, at least in teaching math. So he was lamenting.
Oh, so you're
in
Russian,
teaching-
right? Is he Russian? You see,
Ukrainian.
Okay, close enough to the
Soviet science.
Soviet, exactly.
So he was.
You need to suffer.
He was lamenting the situation that him or a friend was asking a second grader, what is 2 plus 3? And then the second grader answered, oh, it's the same as 3 plus 2 because it's commutative. So basically everyone was learning this beautiful structure and the more abstract thing before they could make sense of how it relates to the physical world. And he was really criticizing that because he was a fan of math being a part of physics, that it derives from the natural world and not from beauty, which is like kind of the opposite
like the
take
abstract.
of what Wigner and Bertrand Russell are saying. Yeah. So there's, I guess it's up to personal taste.
Yeah.
Yeah, I thought he mentions in the paper like Ptolemy's epicycles, which I thought was pretty interesting because it's like I don't know, you probably know the story, but this is great model by Ptolemy of the celestial bodies, which is actually very accurate but completely wrong. It predicted them within 10% error, and it was completely wrong. Like it was insane. I don't remember. I think the Earth is in the center, and it's like all crazy. And the way that it was figured out that it's not correct is very, very careful measurements for many years. There was an astronomer who basically didn't get funded. This is like Europe had many different kings, right? So if you couldn't get funding from one, you would go to a different one. So he left his country. I don't remember. Maybe he was Swiss, let's say. I don't remember. He leaves his country because they refused to fund him. And he goes to the Danish king. The Danish king gives him an island that's very dark. And he like puts some kind of rocks on the island with a little slit, and he measures the positions of the planets every day for years, and then he figures out that like Ptolemy's model is off by 10%.
Wasn't Copernicus?
It might have been Copernicus. I don't remember who it is. Okay. It might have been Copernicus.
At least that's how I know the story.
It's some guy on a Danish. This is how I remember it, but it could be all just slot in Danish for a different. They had a coast because it was an island, but basically that 10% error is where the whole, it's like, okay, we need to rethink this. So it's an interesting, but the problem with quantum physics is they keep measuring it at a higher precision and it keeps being correct, which is extremely disappointing because it's such an uncomfortable theory, but it keeps it's still holding up.
I would claim that any theories, like why this one is uncomfortable, but I don't, classical mechanics is good. They both abstract mathematical concepts.
But in classical mechanics, you can directly map abstract things to physical things, like such as position. That's like very clearly defined. Whereas in quantum mechanics, you need to interpret the math. So that's why people have these different interpretations, like the Copenhagen interpretation of the wave function collapsing, or the many worlds interpretation. It's up to interpretation. That's very different for quantum mechanics compared to classical mechanics. And then in fact, the reason people were converging on or agreeing on the Copenhagen interpretation is because there was a conference, like the Solvay conference.
Yeah, and now it's out of fashion, I guess. But I get what you're saying, but this is because it has like more degrees of freedom in how we interpret what it means. But let's say quantum mechanics, it uses, complex numbers. Right, and they're like, what do they mean? And maybe classical mechanics, you don't need complex numbers. No, so maybe it's easier, but still, it's abstract stuff. We map some abstract math to physical reality. Now we map more complex abstract math to physical reality, quote quantum mechanics. But it's still some mapping.
So you're in the camp. So I think this attitude is encompassed by the quote "shut up and calculate." It's like we don't care like what the interpretation is as long as it's
No, I actually
true.
do. It's interesting. It is interesting. But I think I'll tell you where the mistake. The mistake. It's not the discomfort. I think a lot of physicists, maybe you're in that camp, make like a logical fallacy, right? The fallacy is we have some model of reality, classical mechanics, quantum physics, whatever, and we forget that it's a model of reality. It's not reality, right? All the quantum interpretations, they think, okay, we have quantum mechanics, reality is quantum mechanics, reality is quantum.
No, it's a model.
Let's try to understand what it means. Oh, there's quantum interpretation, many world interpretation, Bohm, whatever, Bohemian mechanics.
Bohemian mechanics.
Whatever. No, I think that's the mistake. That's a model.
Yes,
it's not reality. Yes. Reality is not quantum as it's not classical. It's something else, and we have some mappings. Yeah, that's where I stand. So I'm not in a shut up in calculus.
It's like approximations.
I agree with that.
Yeah. I'm like, it's models of reality, and some are better than others. And that's
they
it?
have their own purview of like where they are valid, their domain of validity. But I think every proper physicist would agree with that it's merely...
Many physicists got angry when I told them. They said, no, the world is quantum.
No, but then that's a bad physicist. If they equate
Cool,
that
okay.
with reality,
Okay.
I would say that's a bad physicist.
Okay,
It's
cool.
a model
So
that
I'm
has,
with you. I'm with
Yeah,
you.
that's not what physics says.
It's also interesting, like if you look
Yeah.
if you look at the development of quantum models and the classical ones. So classical ones were mostly based on your like intuition. For quantum ones, you just, as Xinhui said, you just need to forget, shut up and do the derivations. Like because whatever happens in micro world is so different.
And you have some complex numbers there. How you get intuition about complex numbers? I don't know.
I feel like it's a habitual thing. Like I got used to quantum stuff. Like if you just repeat it often, at some point you just get used to it. It's
like maybe energy levels and colors, you can like kind of swallow that. You know, like that's like almost intuitive or something, but it's
yeah, but the macroscopic world that we derive our intuition from growing up is different from, like you would not run against the wall expecting that maybe the 100th time you land on the other side. You would just not do that.
I think that's why I definitely, at least this is directional. It's not true of everyone, but I do feel like my friends that work on things that have mostly classical models, you know, like optics is very classical, for example.
They age better.
Yeah, exactly. They literally seem to age better than the people that have to deal with, you know, with quantum too much.
You mean there's built-in existential crisis?
Yeah. Like there's like some kind of comfort. Maybe it's it's just maybe more comforting. You know, you run Maxwell's equations through a simulator, you get the modes, you make the waveguide, it works. Like there's no...
It's the same in quantum.
But
There is a mapping between like Schrödinger and some, you know, stuff in quantum mechanics.
But you can't like imagine in your head, like with classical stuff, you can imagine a movie in your head, how it's going, and it like feels good, you know? You can imagine the movie.
But in both cases, it's waves.
But it's like physical
In
waves.
waveguide, you have TE.
Yeah, but these are physical. They're physical waves. The electrons are going like this. You know, it's like very nice. Whereas the Schrödinger waves are waves of probability, which is rough. Like that's
I don't know what electromagnetic waves are. So to me,
What's a probability wave?
I don't know also. I don't know. Have you seen electromagnetic waves? Like, do you have intuition about them?
No, but you can make them, it's easier to make them visible. Like if you take a microwave and you have a standing wave in your microwave, you put in a piece of chocolate, you see where the nodes are. So there's more directly.
Maybe you can do it, but as a regular person, that's not an intuition you get.
Just drop a rock into
I have
the
intuition
water.
about waves. I don't care if they're complex or real waves. Like for both cases, I use math like that is complex in electromagnetics, is complex in quantum.
Okay, I'll let, if you want to go down this rabbit hole, I'll give you an example. So let's say you have a optics where just simple like a lens or like a waveguide or whatever, and you can imagine, you know, the light is shaking the electron, it shakes the one next to it, and it like kind of moves through them, right? So that feels okay, and you know, the refractive index depends on how stiff it is, right? Like it's almost like sound, you know, it feels very, you can imagine some springs and things like that. It feels really physical. Then you take a laser where you have stimulated emission. Why does the light come out the same direction? So you have a photon passing an excited electron. It tells the electron for some reason to fall. I don't know why. Like it comes out of the equations, right? But I don't.
No, but it lasers in both directions. The reason that in a laser
No. Of
goes
course,
one
but
direction is because the other
there's
one-
infinite directions.
Yeah.
Why does it laser just in the direction
Because of the
light?
cavity.
No, I get it. I understand. But why does when a photon stimulates? Let's say a photon is passing in the direction of X, right? When it stimulates another photon to be released, why does it get released along that same axis? Like it's just.
But there's also conservation of momentum.
But
But also you only resonate in the axis.
Spontaneous
for-
emission goes in any direction.
Goes everywhere, but then
why
you
does
select for the mode.
No,
through
but
the
why does
cavity.
stimulated emission go in the direction of the stimulation? Do you see what I'm saying? Stimulated emission is coaxial with the light, with the passing photon.
because Einstein.
But that's very weird. I think it is an Einstein derivative.
yeah, he derived it.
But it's not. That's not intuitive. Like imagine you have a bomb, right? Like an electron in an excited state is like a bomb, and you hit it with a bullet. Why does the bullet come out in the same direction?
No, but I'd assume it's for conservation of momentum reasons, no?
Is that why? But which momentum is being conserved?
There's like several explanations, but I mean it's like basically modes. It's emitted in the modes which are allowed, and then
If it's modes, it's a classical waveguide theory, which is like electromagnetic.
Why is it? What's the mode explanation of stimulated emission?
for the modes, like you're saying, why it doesn't go into
stimulated emission to me.
well, because some of the modes, like between the two mirrors, you enhance the states in which the photon can go.
But if you have spontaneous emission, from a single, let's talk about a single electron. So if you have spontaneous emission when the electron falls, it goes in any direction.
If there is nothing and like no cavity.
No cavity.
Let's say you have a cavity.
No, but if you have a cavity, cavity.
Even changes spontaneous emission?
Maybe.
Yep.
Are you sure? How do I know if I'm a single electron in the cavity? How do I know about the mirrors when I'm emitted?
Because you're a wave, you're not a particle.
No, you don't know. It's I have to travel to the end to feel the mirror.
No, but you're a wave. You feel it already.
Okay.
There's like, in quantum mechanics, it's like density of states. So you go from one pool to another one, and then the probability will depend on how many states are available.
But let's say I'm a single electron. Let's say I just have a crystal and it has mirrors at the ends, just like a laser. Yeah. It's a laser, but it's not on. The laser is not on. A gamma ray or whatever from the sky hits one of the atoms and promotes an electron, and then the electron falls on its own whenever it wants and emits a photon. That's going in any direction. It's not going to the mirrors, right? Like that's just going wherever.
You just need to check in the experiment, man. It goes into any direction in your mind, but in reality, it's not what you think about.
Does that emission, the natural or the spontaneous emission?
Say spontaneous emission. If you have mirrors, if you have a cavity, for sure wouldn't be in all directions.
How big can the cavity be for that to work?
No, but other than that, you do still have conservation of momentum. Like you come in with photons that have a specific momentum, and that needs to be conserved.
That photon keeps going, right, in stimulated emission. So stimulated emission, you put in one photon, you get two. So that one is always conserved.
So you have population inversion.
But Michael, you need to justify like specific conditions. That's why after Einstein described that the stimulated emission, it took how many years to build the first laser?
Yeah.
What was it? Something like half a century or so. So it took a while, experimentalists. It's not that they didn't read that paper, but they were really fighting to tune up those.
To get population inversion and to have it spin itself up instead of die, it just dies. Yeah.
But I would just say back to the main point. Yeah, classical mechanics is more intuitive. I would agree with that. But I don't know, if you have intuition about electromagnetic waves and stuff, I think you can have intuition about quantum mechanics.
I mean, for this one, it's kind of like a semi-classical picture. And then, as you were saying, like as it goes through a waveguide, you have like this kind of the Lorentz model where you have the electromagnetic field of the incoming photon. It is interacting with the atom, but then this has a specific direction, like there's a dipole moment of it. So that should matter in which direction this dipole moment is directed.
It's like a physics therapy, Like I'm like uncomfortable with stimulated emission.
You're uncomfortable
with
stimulated
physics therapy.
I feel like
emission.
Okay.
Too far from the topic of
Okay, so
Eugene Wigner.
Should we read the?
I actually have a better phrase.
The last paragraph.
Yeah, the last paragraph, and I also have another statement by Bertrand Russell. Since we started with it, we can also finish with that. Here. So he said that physics is mathematical not because we know so much about the physical world, but because we know so little. It is only its mathematical properties that we can discover.
Physics.
Physics is actually it's too rich, but mathematics is it's like a simplified version, and the mathematical properties. That's what we can discover.
You're saying that he's saying that physics is mathematical because that's the only part we can understand, or the only. Okay, that's.
He also says, pure mathematics is the poetry of logical ideas.
Cannot disagree with that.
Okay, let's read the last. Dan, do you want to read it or you want me to read it? The last paragraph.
Let me end on a more cheerful note. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend for better or for worse to our pleasure, even though perhaps also to our bafflement to wide branches of learning.